Record. Okay, so today we're going to sort of start first of all looking at the first A-level maths topic. So the first topic in A-level maths is proof. It's quite an interesting topic. It's lots of combinations of actually lots of mathematical properties and information that you've already learned at GCSE and then using them for proof. And proof is all actually just about proving something, whether something's correct or not. But before we sort of get really into the depths of proof and how proof works, we need to go through a few different ways of some terminology and some notation. So the first bit is actually sort of me just going through notation, terminology, go through it quite slowly. And then we will get onto a small bit of actual proof today. And then we will continue more about proof in a bit more depth on Monday. So yeah, proof. Some of this you'll know already, some of this will be new, but just bear with me with it, just so we can go through the whole thing to be happy with it. So proof. Proof, we're going to go through a couple of definitions now, and terminology. So whole numbers. Whole numbers, when we're dealing with proof, are our counting numbers, so 1, 2, 3, 4, 5, 6, 7 onwards, and otherwise sometimes called natural numbers, so number 1 upwards. So whole numbers being 1 and up, well, there are counting numbers, and then whole numbers is when we added 0 to the counting numbers. So when 0 is added to the counting numbers, we then got whole numbers. So whole numbers are 0 upwards, and we obviously don't include anything that is below 0. So they're our whole numbers. This bit is very basic, but it's our 4 rules to positive numbers. It's nice to just sort of remind ourselves of these before we get into the depths of other rules. So proof is based on lots and lots of theorems. So theorems are obviously different rules that we've set and we've proved, and we know they're 100% correct every time. So we have 4 rules to positive numbers. First of all, we can calculate the sum. And again, this is some more of the terminology. So rather than saying addition and rather than saying adding things together, we're using the word sum. So we can calculate the sum of positive numbers. For example, 2 plus 2 equals 4. We can also calculate the sum of several numbers. So for example, 3 plus 4 plus 5 equals 12. You could do it as 3 plus 4 equals 7, 7 plus 5 equals 12. We can also calculate the difference between positive numbers. So for example, 4 take away 2 give us 2. So rather than saying subtraction and addition, in these situations, we're saying we're collecting the sum, calculating the sum, and we're calculating the difference. And as you know, calculating the sum and calculating the difference are reverse functions of each other. We can also calculate the product. Calculate the product, for example, 3 multiplied by 3 would give us 9, and 9 would be our product. So the sum is our answer, is our positive number. So it's 12. Our difference between 4 and 2 is 2. Our product of 3 multiplied by 3 is 9. And we can also calculate the quotient. And we can do this by division. So 9 divided by 3 would give us 3, which is our quotient. And again, the product and the quotient are reverse functions of each other. That's nice and simple, really basic. And then we go on to integers. So integers, these are our negative and positive numbers. And in these situations, 0 is the origin. It is neither positive nor negative. And it's really important to remember that. We often refer, obviously, to the origin on a graph as being the point where the 2 zeros meet, the intercept, and 0 is the origin. So it's neither positive nor negative. And we're going to look at 4 rules to negative numbers. Again, basic recap, but it's really important that we do go through this. So when we are adding negative numbers, it is the same as subtracting positive numbers. So for example, 5 plus minus 3, or 5 plus negative 3, equals the same as 5 minus 3, which would equal 2. So it's the same as subtracting positive numbers from each other. If we're adding on a negative number, this is the same as subtracting positive numbers. In reverse, if we are subtracting negative numbers, it is the same as adding positive numbers together. So 5 minus negative 3 equals 5 plus 3, which equals 8. And then just the last couple of rules for multiplying by negative numbers. If you are multiplying two positive numbers together, you get a positive number. If you multiply two negative numbers together, you get a positive number. And if you multiply a positive and a negative number together, you will get a negative number. Similarly, dividing by negative numbers, dividing two positive numbers together, you'll get a positive number. Dividing two negative numbers together, you'll also get a positive number. If you're dividing a positive and a negative number together, you will get a negative number. So these are just a few little quick recaps. So real numbers. So again, we have to, this is another terminology that we need to know what we're actually talking about here. So we've already spoken about the fact that we've got whole numbers, got counting numbers, now we've got real numbers. So under the subheading of real numbers, we have integers, rational numbers, and irrational numbers. So rational numbers, irrational numbers, and integers all fit under the category of real numbers. These are all real numbers, which then probably poses the question, what is an unreal number then? Well, an unreal number is an imaginary number, which is a bit of a strange concept to sort of get our heads around. Basically, it is a made-up idea that we use for complex maths. So, for example, infinity and square root of -1. These are made-up ideas. They're not actual physical numbers that we can get. So it's a bit of a strange concept, but they're unreal numbers. So unreal numbers are things like infinity, so on. So actually, let's look at two particular real numbers. Let's look at rational and irrational numbers. Let's look at rational numbers first. So rational numbers, they're actually, you can break rational numbers down into a ratio of integers. So they can be a decimal and they can be a fraction. So rational numbers can be decimals, they can be fractions. So it's P over Q. So all integers can be written as a fraction whose denominator is 1. So integers and counting numbers are rational. So rational numbers can repeat or they stop. So they can repeat or they stop. So it's either a number that just keeps repeating and repeating and repeating and repeating. So for example, 0.66 recurring would be a rational number, or it is a number that stops, for example, 0.6. So that is a rational number. It's the decimals, the fractions, and numbers that actually stop. On the other hand, we have our irrational numbers. So our irrational numbers are numbers that either do not repeat or they do not stop. So for example, pi is an irrational number. So 3.141592654 continues. We have our three dots are ellipses. That means that is a continuing pattern for the numbers, and numbers will continue. It just means that we have just shown a small subsection of those numbers. Another example of an irrational number is if our square number, square root, if it's not a perfect square, is a decimal that does not stop or repeat. So square root of a number, if the square root of a number is not a perfect square, it is a decimal, but then we'll get a decimal, and these does not stop or repeats. So it doesn't stop or it doesn't repeat. So that would give us an irrational number. So now we're going to look specifically at notation. Lots of this notation will be quite new to you, and it's really important because actually what we start to do now at this point in maths is we start to, especially in proof is actually writing almost a story of, you get given a sentence to prove this, and you need to show logically in steps how you're proving it. So you're writing a story, but you're writing a story in maths. So we start to use lots of these more complicated notations, these symbols, to give us a shorthand for writing things and also make things clearer. So rather than like being slightly complicated and going, oh, well, this is sort of like that and it sort of means this and that, we have really clear notations that has set meanings. So we're going to talk about sets of objects first. So sets. Sets are collections of objects. So a collection of something, collection of an object. And our objects, we call them elements. So a set is a collection of objects, and the objects are inside the set, we call elements. And if we are writing a set, we write a set with curly brackets. So for example, 2, 3, 4 is the set inside those curly brackets, and it is a set that contains the numbers 2, 3, and 4. You could then get asked to show a set. So we've got it in the curly brackets, positive even numbers below 5. So then that is our set. That's our rule for our set. We then have equals, and then in our next set of curly brackets, we have 2 and 4 because they are our 2 positive even numbers that come below 4. So you can have a set equaling a set. So you can have rules inside a set that then equal our actual set. So we show them what our elements are of that set. So some more notations that we use in sets is we have our universal set notation. This symbol, if you see it anywhere, means that it contains everything. So the universal set contains absolutely everything. Then we have our empty set notation, and that means there is no elements to this set. Then we start having this part in. So if element E is in a set A, we would have this notation. So E is in set A. And then we could write this way, instead of writing element D is not in set A, we can write this instead in our shorthand, D not in A. So we can see we have 2 different symbols that we're going to use for in a set and not in a set. So you can start to see how when we're using proof and how we're going to write these stories about the maths, that we can start to use this terminology, these annotations to help us. So we could use empty set, we can use the symbols for in a set, not in a set, rather than lots of words which can start to complicate and make things a little bit messy. So we can use rules. So we can say A equals x to the ratio x squared equals 4. So x ratio points means all values of x, such as A equals -2 or 2. So if x squared equals 4, that means that x means all the values of x such that, so all the values of x such that x squared equals 4, well, our possible options for there is -2 and 2. So again, we would write them in the bracket. So A would equal -2 and 2. So that is our rules, and then that would be our answer. So number of elements. So if we're talking about how many elements are inside our set of rules, our set of objects, our set, we can use NA. So for example, N in our normal brackets, then our curly brackets of 2, 3, 4, close both sets of brackets, equals 3. So we've got 3 elements inside that set. So N would equal 3. Now we're going on to subsets. So we can actually then start breaking our sets into small groups. So we can have sets within other sets. So we could say set A is a subset of B if all our elements in A are also elements in B. So for example, set A is 2, 3, and 4. So we can make the subsets of A 2, 3, 2, 4, 3, 4, 2, 3, 4, and 2, 3, and 4. Now, 2, 3, and 4 actually has a different name and terminology for it, because actually 2, 3 and 4 is the same as the original subset. So here our 2, 3 and 4, oops, is the same as our original subset. It's the same as our original set. So 2, 3 and 4, we actually call it, we say it's not a proper subset of A, because A equals A. So we say it's not actually a proper subset of A. And then we can use this notation to help us. So we can use this notation here to demonstrate that A is a subset of B. So for example, 2, 3 is a subset of B. So A is a subset of B. We can use this one here for saying A is a proper subset of B. So 2, 4, that would be a proper subset of B if B was 2, 3, 4. And then C is not a subset of B. We have our set symbol again, and then we have a cross for it saying it's not a subset of B. So here is an example. So we have A, 3, 5 and 6. So that's set A. B is 1, 2, 3, 4, 5, 7, 8, 9. So is B a subset? Is A a subset of B? Well, let's have a look. 3 is in B, yep. 5's in B, yep. 6 isn't. So A is not a subset of B. So we have our subset symbol, and then we put a line through it saying it's not a subset. So A is not a subset of B. So then we can go on to set notation again. And we use a Venn diagram to help explain this part. So a Venn diagram shows us a union of two sets of objects, two sets of elements. So a union of two sets, we can use this symbol. So we have A, U, B. So U for our union, and that is things that would occur in A or B or both. So that is our union of two sets. So for example, let's pop, what am I going to do? I'm going to write odd in here. Let me put my annotation on. Annotation. So we're going to have odd numbers in here, and we're going to have numbers less than 10 in here. So we might have 26, might have 1, 21, 4, 6, 35, 3, 5. So there's a few numbers in there. So we would say that the union of the two sets, so we'd ignore 26 because 26 isn't the union of two sets, but actually everything inside A, everything inside B, and everything inside A and B is the union of the two sets. So it'd be A, U, B, A union B. So that's the union of the two sets A and B. Our intersection, so where they overlap, the things that are in A and B, so our numbers 1, 3, and 5 would be, we would use this notation to show the intersection. So things in A and B. Then we have our universal set again. So we had this symbol before. This contains everything inside the rectangle. So this, if we had a universal set, would also include the number 26. This is the only notation where it would include the number 26. All the others would include the other ones there. So let's get rid of that. So in the Venn diagram, in which section will the number 2 go? Well, the number 2 is not an odd number, so it wouldn't go in B. So it can't go in C. It's not a number, it is a number below 10, so it would go in section D for us. So then we go through standard sets of numbers. So we have natural numbers. So this is annotation for natural numbers. Natural numbers are our counting numbers, and our whole numbers. And we use a notation n. So if a number is a natural number, we write this notation. Then if we have an integer, so we use the z as the notation for integers, and we have nez, and that is for saying our number is an integer. We have z plus, that means our integer is a positive integer, and if we have n plus 0, it means our integer is positive, and actually, or our integer includes 0. Also have notation for rational numbers. So rational numbers, we use q. So any q is our number is a rational number, but we can also show it using this rule. So q equals p over q, meaning that p is a integer and q is a positive integer. Rational numbers we notate with an r. So any r would be our number is a rational number. So notation in mathematical arguments. So this is now going to help sort of those joining points. So we might want to say therefore, so actually this mathematical theorem proves this and this proves that. So we have this new notation, this double arrow. And so the x to the y with a double line on the arrow, that means implies. So we can use it in this way where we have x equals 5. Therefore, that implies x squared equals 25. If we know that x equals 5, that implies that x squared must equal 25 because x equals 5. We also have a double-ended arrow, so xy, and that means equivalent to. So x squared minus y squared equals 9, and that whole equation is equivalent to, that should be in brackets, x plus y multiplied by x minus y equaling 9. Then we get the 3 dots pointing upwards, and that means therefore. These get used a lot in chemistry as well, and for shorthand notation, it's just a lot easier than having to write things like therefore, but we're actually then using full sentences, but using notation. So x equals 2a, therefore x is even. So we're we're just trying to eliminate the use of written words as much as possible. So x equals 2a, therefore x is even. And we can have because, which is the same 3 dots but upside down. So we can have x squared plus 1 equals 5 and x equals 2. So as a full sentence we can write because x equals 2, x squared plus 1 equals 5. So you can see there's proof now. This is how we're getting behind the idea of proof. So we can't just, if we had x equals 2 and then write x squared plus 1 equals 5, you're not having that proof behind it. By putting in the because, we're saying because x equals 2, x squared plus 1 equals 5. So mathematical proof. I'm going to go through, probably actually going to end up a little bit shorter than an hour today, but we're going to go through what mathematical proof is. So mathematical proof, it is a mathematical argument that explicitly shows that a given statement is always true. And so we have these two things that we use. We use theorem and we use conjecture. So theorem is a mathematical statement that has been proven to always be true. So a theorem has been proven to always be true. Whereas a conjecture is a mathematical statement that has not yet been proven to always be true. In proof, you'll be asked to prove a conjecture. Now we can use theorem to help us prove a conjecture, and that is generally the basis that we work on proof, is we'll be given a conjecture and we need to prove it, and we can use other theorems which have been proven to always be true to basically then prove our conjecture. So we work on the idea of assumptions. So assumptions are conditions under which the conjecture is true. So an assumption is that a conjecture holds for all positive integers. So therefore, if we know an integer is positive, the square is also a positive integer. We use this fact as a step in proof. My fire alarm appears to be going off. So I'm just going to pop back in 2 seconds. Nope, it's gone. It's fine. So we use this fact as a step in proof. So we use assumptions as a step in proof. So we use these conditions. So we go, okay, so this is always true. This is always that. So this is going to be a step in my proof. Just going to go through a couple more ways that we write in proof. If we are using even numbers, if we wanted to say, for example, if you're being asked to prove that if a integer is positive, the square is also positive, or if we're being asked to prove two even numbers added together equals an even number. If we're writing even number, rather than writing words even number in proof, we write 2n. If we're writing odd numbers, we will write 2n plus 1. And if we're writing consecutive numbers, we'll write n, n1, n2, ... for our ellipses to show that it's continuing. So here's an example. So if an integer k is divisible by 10, how can we write this in proof? Well, how we would write this in proof is k equals 10n. So we would use 10n because n is our number, and that would mean 10 multiplied by n would also mean that n is divisible by 10. So therefore 10n, n is our integer, k is showing that that n is divisible by 10. So we're going to go on to the first little bit of proof. So we are actually probably definitely going to end a bit early today, but no worries. And we're going to do proof by deduction. And what we do with proof by deduction is we begin with a known theorem. And we use a series of logical steps to go from our theorem to our final statement. What is really important is you need to write each step clearly and consider all potential cases. That's why all that notation I've gone through at the beginning is really, really important that you learn and know, because that takes part in your writing your steps clearly. That is actually where most of your marks will come, is actually writing all your steps down clearly, writing that notation down and considering all our potential cases. Then eventually you will get to a final closing statement. And this final closing statement should either prove that conjecture is always true or that it is false. So here is an example. You're asked to prove that the sum of two odd numbers is even. Oh, and so we're going to work through this one together. So you're asked to prove that the sum of two odd numbers are even. So we're going to start off with some assumptions. So we are going to start off like this. X plus y are odd. So we're going to assume x and y are odd. So if x and y are odd, we're going to write them using the notation before. X equals 2a plus 1. So that means it's odd. So it's like for 2n, it's like the n plus 1, but it's 2a plus 1. And y is odd. So y equals 2b plus 1. In this situation, a and b are integers. Okay. Now we're going to go on to sum, which is what we said before. So we can actually sum these together. So we look at these and go, okay, so if we did x plus y, these are whole numbers, these are positive numbers, we can sum these together. So x plus y, well, that would equal 2a plus 1 plus 2b plus 1. Then we can simplify that. So we can actually go, okay, well, that equals x plus y equals 2a plus 2b plus 2. So by collecting terms, what we've done by collecting terms is actually, this is a really important step in proof. By collecting terms in a sum, what we have done is it's a known, this is known to always be true. So it's a valid step in proof. So if we can collect our terms in a sum, we are proving this is always true. So we're saying 2a plus 1 plus 2b plus 1 is 2a plus 2b plus 2. Okay, so by collecting terms in a sum like this, is known to always be true. And this is a valid step in proof. So this is a really valid step in proof, is actually collecting those like terms. We've collected those terms together. So we've said x plus y, so these are our odd numbers, we don't know what they are. That equals, so x is 2a plus 1, y is 2b plus 1, so actually x plus y equals the same as 2a plus 2b plus 2. So we can start to see what's going to happen. All these numbers here are going to be even numbers because we've got 2 in front of all of them. So then, next bit, we haven't actually got to the end of the proof yet. So we want to go on to inspection. So that's our third step. So we go, okay, so we've got x plus y, and we have x plus y equals 2a plus 2b plus 2. Okay, well, what actually can we do to this? Oh, okay, so I can actually say x plus y, that equals, well, we've got 2 multiplied by all of those. So 2 here, pop some brackets on, 2a, so 2 multiplied by a would give me 2a, so that makes that. 2 multiplied by b would give me 2b, 2 multiplied by 1 would give me 2. Okay, so x plus y equals 2, a plus b plus 1. Well, in this situation, we know a and b are integers, therefore 1 can be an integer as well. So if we add them all together, a plus b plus 1, well, we can say actually they're an integer altogether. So x plus y equals 2c, 2 whatever is in here. So that is the same as saying x plus y equals 2a plus 2b plus 2 equals 2a plus b plus 1. So then we come in with our final statement. So our final statement is, so we're showing here that it's 2c, so we've got an even number here. So we're saying no matter what we do, every time we add these odd numbers together, we are getting an even number. So our final statement is the sum of 2 odd numbers is an even number. So if we were going to write down every single step of this as the full proof, it would look like this. Oh, no, go back. Clear. So write it down as full proof. So as a full answer, it would look like this. We would write, oops, draw. Oh, what's happened? If x and y are odd numbers, x equals 2a plus 1, y equals 2b plus 1. Here, a and b are integers, a and b are integers. Therefore, x plus y equals 2a plus 1 plus 2b plus 1, which equals 2a plus 2b plus 2, which equals 2a plus b plus 1, which equals 2c. So x and y x plus y, sorry, I'm doing x sum y, so x plus y is even for all odd x values and y values. So there is 5 steps to proof that you must always include, and these are our 5 steps. So our first step is our conjecture. That'll be our question. What do you need to prove? So that is the first step. That is your question. What is your conjecture? What do you need to prove? Then you have your second step, the theorem. That is the theories, that's the stuff that we know is 100% true, that we are going to use to help us prove our conjecture or disprove our conjecture. Then step 3, we're going to work through logical steps. Actually, we're going to use our theorems, we're going to work through all this in logical steps to either prove or disprove our conjecture. So we're going to go in logical steps. 4, we're going to look at assumptions. Well, if this means this and this means that, that must mean that, basically. Assumptions, and then finally we have our final statement. So, for example, at the bottom, x plus y is even for all odd x and y. Final statement. And let's go through one other example of proof by deduction. So this time we're going to do prove that the sum of two even numbers is even. So step 1, we've got x equals 2a, y equals 2b. So this is our notation again that we need to be familiar with. X and y, and our a and b are our integers. So we're going to pop here where a and b are integers. So step 2. Okay, so it's proof that the sum of two even numbers is even. We're going to add our integers together. So we're going to have x plus y, and that will equal 2a plus 2b. Let's look at it again. So we've got x plus y. Well, that will equal, let's expand some brackets here. Let's make some brackets. So we're going to factorize this. We've got 2a plus b. Step 4. Well, we can say here, since a and b are integers, b is also an integer. So since a and b are integers, a plus b is an integer. So finally, so the sum of two even numbers is an even number. And I've got one more example to go through with you for proof by deduction. So our final one is prove that x squared minus 4x plus 9 is always positive. So we'll look at this and go, okay, well, what would we do? Well, let's deal with the squared part. So let's have a look. So x squared, let's expand these brackets. So let's put x there. X minus 4x. Well, okay, so we've squared x here. So 2 lots x by x minus 4 lots of x's together. So actually it's x minus 2x. Square that. We're going to get rid of our 4 here, make it a 5. Is always positive. So x squared minus 4x plus 9 is always positive. Well, let's have a look. So x squared minus 4x plus 9. Well, work this out. We've got x minus 2x. No. Right, let's undo this and do this again. So we've got x minus 2. I'm going to get rid of our x here. We're going to cancel them out. X minus 2 squared plus 5. Okay, well, this is going to be positive. And this always retains positivity. So this helps retain our positivity. So what I'd like you to do with this one is positivity. Is you've got the answer here. I want you to work through all the different steps of proof to find out how we would get to this answer to get this proof. I didn't realise I was going to get through this so quickly. So I'm actually going to leave that there for today. And then we will pick up on Monday. And on Monday, we will do proof by a few different other methods. What I'm going to do is send over some questions for proof by deduction, for you to have a go at working at. And it's really about the method and the process and using the notations and making yourself really happy and familiar with them. So I'll pop this on YouTube as quickly as I can. I will send over those questions. And yeah, I hope this was really useful for today. So